Okay, well, we're back with our third part of this series of videos on problem solving and applications of linear relations. We talked in video 1 about some general techniques. Video 2, we applied these to some number puzzles, and now we're going to get to some more realistic, useful problems in this video where we talk about some applications involving velocity or speed. So just to review our 6 steps, we're going to read the problem to get a general understanding, and then in step 2 we're going to reread the problem and organize our information as we go. We're going to write down the known and unknown values both in words and in mathematical symbols, either numbers or variables or variable expressions. We will perhaps do this in a table or chart, or perhaps just in columns. We'll draw a picture, if useful, or a graph and label its parts. Write down a formula or equation or inequality for the system. Once we have it organized in step 2, then that should be able to help us write the formula down or equation that we need. Then we'll solve that equation or perhaps a formula or inequality or system for the information we need. And then we will write down our answer back in sentence form, including our units, and interpret our answer. And finally we will check both to see if it makes sense and then also to do an exact check going back from using our answers that we've come back with, go back to the original problem and work through the logic of the problem again. So the class of examples that we're going to look in here are distance, time, velocity applications. So remember that the slope is an average rate of change. So a large number of applications involving linear models where the rate is given or is to be solved for. So recall that the units of the slope are the units of y divided by the units of x. Remember, slope is delta y over delta x after all. So notice that when you multiply the slope by the x value, the units of x cancel out and you're left with the units of y. So for example, if y represents distance in miles and x represent time in hours, the units of m, the slope, are miles per hour, and so m is the rate of speed or the velocity. In this case, mx, multiplying the slope times the x value, is then the distance traveled. Sometimes people will change the letters and write rate times time equals distance. So the rate is the slope, which is the rate of speed, and then of course time is the input, that's your x, that's your first coordinate, and that equals the distance traveled, the second coordinate. Now that gives you of course a linear relationship, and this assumes if you start at some zero position. If you want to find your position rather than the distance traveled, then we need to add on our initial position, which is our y, adding on a y-intercept, and that gives us a general kind of a linear formula. So let's look at an example here. A person is traveling from UA Fort Smith to Memphis. He noticed at exactly 12 noon he enters I-40 at mile marker 7. He sets his cruise control for 70 miles per hour, and we're going to make a really unrealistic assumption here that the traffic is such that he is able to leave his cruise control set for the entire duration of the trip. He's not going to pull off the highway he's not going to slow down or speed up for the entire trip until he gets to Memphis. Pretty unrealistic set of assumptions there, but we're going to use that for what we're doing here. So then, if that's true, then what is the formula that expresses his position as a function of time? Make a table showing his time on the hour. Where will he be at 3:20 p.m.? At what time will he be crossing the Mississippi River into Memphis, essentially at mile marker 286? And what's the appropriate domain for this particular function that we come up with, the formula that we come up with? Okay, so let's go ahead and work this. Let's start with the first part and see if you can press pause and work that out now. Well, hopefully you notice that since we have a constant rate of speed, that's a constant slope of 70 miles per hour. M is a fixed amount at 70 miles per hour. Okay, and that it's linear. And so we're going to use some more suggestive letters for the other parts. Instead of y, we're going to use p for position in miles from the Oklahoma border, which is basically the mile markers on the interstate. And t is going to be time in hours since 12 noon. And so then we get p of t equals mt plus p sub 0. P sub 0 is 7 because that's where we started at time 0, which is 12 noon. And m is 70 miles per hour. So p of t equals 70t plus 7, and that's the answer to part A. Now if we make a table of is time on the hour. Time is noon, 1 o'clock p.m., 2 o'clock, 3, 4, and 5, if we go that far, for example. Then we get the mile marker, we get the time t is then 0, 1, 2, 3, 4, 5, and the position starts at 7, and it goes up by 70 miles each hour, so that's 7, then 77, 147, and so forth. If we continue on, where will he be at 3:20? So now we're solving an equation. First of all, we need to know what the t value that goes with this. Now, we have to be careful here a little bit because our t value, we're probably going to enter it in as a decimal, but minutes are not tenths of an hour or even hundredths of an hour. They're 60ths of an hour, so we need to do a little unit conversion here. So we have 3 hours and 20 minutes. 3:20 p.m. is 3 hours and 20 minutes. No, I did this at 1:20. Okay, so let me go ahead. I'm going to do something here that you can only do if you're the teacher, and that is I'm going to actually change the problem to match the way I did it here. So we're going to go back here, and I'm going to change this to 1:20. So when you're the student, you can't just go along and change the problem to be what you want, but if you're the teacher, you can. So here we go. 1:20, and then everything will work out correctly. Okay. Okay, so at 1:20, it's 1 hour and 20 minutes past the time of t0, which was noon. So 1 hour plus 20 minutes, let's get it just to be hours. So the 20 minutes part is 1 hour. You multiply by 1 hour over 60 minutes. The minutes cancel and we get hours, and that's 1/3 of an hour. So it's 1 plus 1/3 is 4/3 hour, or 1.3 repeating hours. So what we're now wanting to find is p of 4/3. So we plug in 4/3 for t. So 70 times 4/3 plus 7, that works out to be 100.3 repeating miles. So at 1:20, he will be 1/3 of a mile past mile marker 100, or in other words, 100.3 repeating miles east of the Oklahoma border along I-40. Okay. At what time will he be crossing the Mississippi River into Memphis? This is basically at marker 286. So notice in part C, we basically knew an input and we were trying to find an output. In part D, we know an output and we're trying to find an input. So the output 286 is put in place of the position, and we want to solve for t. So subtract 7 and divide by 70. That works out to be approximately 3.985714. Actually, then it's a 2, and then it repeats at the 857,142 repeats, but approximately 3.98 something hours. And if we take subtract the 3, so that's the 3 o'clock, 3 hours, and take the 0.985714, etc., and multiply that by 60, that turns out to round off to 59 minutes. So that will be 3 hours and 59 minutes after we started. Since we started at noon, that will be 3:59 p.m. So right at 4 hours to get to Memphis if he can go without stopping and go 70 miles an hour the entire time. Now, what's an appropriate domain for this function? Well, if we just look at the formula, p of t equals 70t plus 7, there could be, it looks like it could be all real numbers for the domain, but so there's nothing in the formula itself to restrict the domain. But the context of the problem does restrict it. The lowest allowable value for t is 0, since at t equals 0, the car first entered the interstate. Before that, position along the interstate doesn't make any sense because our car wasn't driving on interstate I-40. Furthermore, the numbers are reset at each state line. They increase on the even-numbered interstates. 0 at the western end, and they increase as you go to the east, and then they're reset. So it'll be reset to 0 at this Tennessee state line. So we need to. So this only really works till you get to the Mississippi River. But then at that point we're actually at Memphis, so essentially our trip is more or less over. So what we want to do is go from a time value that goes from 0 up to when we get to Memphis, which we saw was about 3.9857, whatever. So if we round this off to 3.986 or 57, I probably should say, then that's a pretty good time. So somewhere, anywhere, any t values in there, then this formula will give us our mile marker. Okay. Let's do another problem here. Sam leaves Van Buren at 2 o'clock p.m. traveling east at 75 miles per hour. Bob leaves Van Buren at 3 o'clock p.m. traveling west at 65 miles per hour. At what time will they be 200 miles apart? So notice if we let t equal the time in hours since 2 o'clock, the earliest time somebody leaves, t is also the time Sam has been on the road. However, Bob has traveled a smaller amount of time than Sam since he starts later. So we are assuming let's just assume they're traveling at a constant rate of speed. The distance each person travels, the distance from Van Buren, is a linear function of time. And since both travelers start at Van Buren, the distance from Van Buren is just a multiple of the time traveled. So if we think of the distance as being the distance from Van Buren, they both start at 0. So the distance each traveler from Van Buren is a function of time will have the form rate of speed times the time traveled equals distance traveled. So we set up a chart, and we set it up that way so that the one column is rate of speed, then the time traveled. We multiply those values in those two columns to get the last column, which is distance traveled. So this is going to be typical of many linear application problems where we multiply some columns together to get the last column on the right. Sometimes we'll also have to add to that a constant term if they're starting at different positions. But here they're starting at the same position, so we can just take that constant term to be 0 and not have to worry about it. Now since they're going in opposite directions, the distance traveled will add up to be the total distance between them, and that relationship will give us our equation. Okay, so here's our problem again. Sam leaves Van Buren at 2 p.m., traveling east 75 miles per hour. And Bob leaves Van Buren at 3 p.m., traveling west at 65 miles per hour. At what time will they be 200 miles apart? So if we let t equal time since 2 o'clock in hours, then we have our travelers, Sam and Bob, and then we have a total distance. The slope is the rate of speed in miles per hour, and for Sam that's at a constant 75 miles per hour and Bob at 65 miles per hour. Now the time that Sam travels is t, because it's from 2 o'clock till whenever, and that's t. So the distance he travels is the miles per hour times hours gives you miles, and that's the distance traveled. So it'd be 75 times t. 75 miles per hour times t hours is 75 t miles traveled. Similarly, Bob is 65 miles per hour times his time traveled will give his distance traveled. But notice that Bob leaves an hour later, so he has 1 hour less on traveling time than Sam does, so his value is t minus 1 for the time that he's traveled. And so then the total distance that Bob has traveled is 65 times parentheses t minus 1 close parentheses. Now the total distance apart is 200 miles. Now since they're going in opposite directions, the total distance they are apart is the sum of the two distances traveled. So that gives us our equation, 75t plus 65 times t minus 1 equals 200. Distribute the 65 to get 75t plus 65t minus 65 equals 200. Then combine like terms, 75t plus 65t is 140t, and then I also subtracted or added 65 to both sides to get 140t equals 265. Then solve for t by dividing by 140. That fraction reduces to 53 over 28, or approximately 1.89285714. Actually, at that point it repeats back to the 285714, 285714. Okay? And if you make that in hours and minutes, you've got 1 whole hour. Take that away, then take the 0.892857, etc. Multiply that by 60 minutes per hour. The hours cancel, and you're left with, well, if you round off to the nearest minute, 54 minutes. So it's 1 hour and 54 minutes for the t value. So they will be, now of course, what time of day is that? T is the time since 2 o'clock, so that's actually 3:54 p.m. So they will be 200 miles apart at 3:54 p.m. So let's check it. We can sort of check it by sort of recreating our table here. Sam is going at 75 miles per hour. He traveled for t hours, 1.89 whatever hours. Multiply those together, he traveled 141.96 miles to the east. And Bob is going to the west, so he traveled 65 miles per hour times 0.9 or 892857. Of course, I got that by subtracting 1 from t. And that gives him a distance of 58 miles, 58.04 miles. Add those two distances together, that's 200 miles, because they are going in opposite directions, so the distances add up. Alright, let's take another example. Fred leaves Van Buren at 2 o'clock p.m. traveling east at 55 miles per hour. His wife, Wilma, notices that he forgot his briefcase, so she jumps in the car and leaves Van Buren at 2:30 p.m. and travels east at 85 miles per hour trying to catch him. At what time will Wilma catch up with Fred? Assuming they both maintain those same speeds. See if you can work this one out. It's kind of similar to the last one, a little bit different in the way you set your equation up, but very similar in the way you set your table up. Go ahead and do this one now. Press pause. So notice again we're going to let t equal the time since 2 o'clock in hours, and we have Fred and Wilma are our two travelers. Fred's going at a constant rate of speed of 55 miles per hour and Wilma is 85 miles per hour. So that means that their distances traveled are going to be linear functions because that rate of speed is the slope, which is constant. And if we let t be the time since 2 o'clock in hours, the time that Fred travels is t. But Wilma doesn't leave till half an hour later, so her time is t minus 0.5, or t minus a half if you'd rather use fractions. Now the table is set up as we often like to have it, where we multiply the slope column and the time traveled column, the rate times time, to get distance, which is the last column. So we multiply the two previous columns to get the last. So 55 times t is 55t, which is the distance Fred travels. And the distance Wilma travels is 85 times parentheses t minus 0.5, close parentheses. So notice they're going in the same direction, and what we do know is that the times are different, the speeds are different, but the distances will equal at the point where Wilma catches up with Fred. So we have 55t equals 85 times parentheses t minus 0.5. So now we have our equation. To solve that, we distribute the 85, and you can see that's 85t minus 42.5. Then I subtracted 85t from both sides to get negative 30t is negative 42.5. Divide by negative 30 on both sides and get t as 1.41666, the 6 repeating. Hours, okay, and of course we've got the 1 whole hour, and you take the 0.41 and a whole bunch of 6's repeating times 60 minutes per hour, and that rounds off to about 25 minutes. So 1 hour and 25 minutes. That's after 2 o'clock, so that will be 3:25 p.m. So Wilma will catch up with Fred at 3:25 p.m., 1 hour and 25 minutes after Fred left, assuming, of course, that he's on the road that long. And Wilma will have traveled half an hour less than that, so that's 0.916666. So she will have traveled a little less than an hour, actually 55 minutes. to catch up with him. And they will both have gone about 77.9 miles. And you can kind of see the check down there in the bottom. Mike and Alice both leave Fort Smith at 6 a.m. traveling east. Mike maintains a speed of 75 miles per hour and Alice travels at 68 miles per hour. At what time will they be 90 miles apart? Okay, see if you can work this one out. Press pause now. Well, very similar setup as to before. This time, the time t could be measured since 6 o'clock in hours, and they're eventually going to be 90 miles apart. So you have the travelers Mike and Alice. Rate of speeds are 75 miles per hour and 68 miles per hour respectively. This time, the two times are the same. They left at the same time, so it's just t is the time they traveled. So Mike will have traveled 75t and Alice 68t for the distances traveled. Now they're going in the same direction, so the distance that they're apart is the difference in the two distances. And of course Mike is the fastest, so he's going to go a little farther in the same amount of time. So we get 75t minus 68t has to be equal to the 90 miles. So of course combine like terms in the left there. Essentially factor out the t and add the coefficients. 75 minus 68 is 7. So you get 7t equals 90. Divide by 7, we get t is 97ths, or about 12.86 hours. And that's about 12 hours and 51 minutes. Again, to get that 51 minutes, you subtract the 12, take the fraction part, 0.857142, etc., and multiply that by 60 minutes per 1 hour to convert the hours, the fraction part of an hour, into minutes. And I just rounded off the nearest minute, so that is 12 hours 51 minutes. And that's after 6 a.m., so 12 hours later would be 6 p.m., and then it's 51 minutes after that, so it's 6:51 p.m., and that's when they'll be 90 miles apart. So both of them will have traveled this 12.857 whatever miles, or hours, times 75 miles an hour means that Mike has traveled 964 miles, 964.3 miles. Alice then at 68 miles an hour times 12.8571429 miles or hours gives you a total of 874.3 miles. And so the difference in the two, sure enough, is 90. So that does check. So we've seen some examples here using velocity problems. In the next video, we'll come back and try to apply these same steps, 6 steps to solving application problems. We're going to apply those to some unit value problems in the next video.